Alrighty, so we're back here having a closer look at our RM3 fluid heater. So what I decided to do, before I spent too much time wiring the thing up, even for a more general test, was to just very quickly see if it actually powers up. So just to run through the main components, we have the main heater itself here, which is essentially a tank, a heating element and some electronic control circuitry. Now the reason that it has electronic controls in there is because if you have a look at the rating plate here, I don't know if this is going to come out, but what it basically says is 4000 watts, 200 to 450 degrees, 200 to 450 volts DC, 70 degrees centigrade and max 0.45 bar pressure. Now the reason it needs a control circuit is to allow it to work over such a broad range of DC voltages and still produce the same power. Because for example, if the heater were designed to run 4 kilowatts at 200 volts, when we, let's say, wanted to put 400 volts into it, it would start trying to produce 8 kilowatts and would burn itself out in fairly short order. And again, likewise, if we designed it to run 4 kilowatts at 400 volts, we took it down to 200 volts, it just wouldn't produce the right amount of power at all. So what they do is, from what I can ascertain, they design it to run 4 kilowatts at 200 volts, and they then use a little PWM circuit to reduce the average power going to the heater as we increase voltage above 200 volts. Now that does have one potentially major implication for us, that our system voltage in the land yacht is only 160 volts DC. So on the surface of it, we're below the minimum voltage. Now if the circuit had been designed in such a way that it detected that voltage, we would be in trouble. Fortunately, that doesn't seem to be the case, and the heater will pretty much work on a lower voltage but predictably produce slightly less heat. Now if we do the maths, at 160 volts we're just shy of 3 kilowatts. So I'm thinking, with a bit of luck, that'll be more than enough to heat our fluid for our cabin heater. So also on the side of the tank is this 12 volt pump. This is a Bosch PAD pump, which I had to purchase separately on eBay for a not very cheap price, but these are the type of pump that don't have a connection between the impeller and the motor. They're this magnetic coupling system. Now I have ran that pump here dry and it makes a nasty screeching sound, so I'm really hoping that that's just because it's dry, and when we get some liquid in there we should be fine, hopefully. What else have we got? So there is a three-way terminal, we can get this off, that is, on the top here where the signals connect, just a little bit tight, and I guess that's on there to stay. There we go. So there's just three-way terminal on there. I'm very fortunate, as you can see here, this is a plug that pretty much clips straight on. This is a fairly common automotive connector, and indeed I was able to find a matching plug on the land yacht's wiring harness. that had been obviously on some sensor or some other, and now it's not going back. Oh, there we go, and it clips in. So yeah, I was able to find that plug on the Land Yacht's engine harness from a sensor or some such that wasn't being used. So if you need a plug for this, you can pretty much get one from, I would say, any BMW or probably other cars that would utilize the same plug. But that being said, it gives us then 3 wires. So there is a bit of info on these on the web, and the chap that I bought it from actually was kind enough to tell me the connections. This one here on the left, or closest to the center of the unit, is ground. The center terminal is 12 volts to turn on, and this one on the right is a fault output, which is just an open collector transistor. So you could connect a little LED and a resistor or something to that. So if the thing there's a PIC microcontroller in there, so I'm sure there's some kind of, you know, if it overheated or shut itself down or something, you could have an indicator on there. I'm probably not going to bother with that, to be perfectly honest. So that just needs 12 volts supplied to it to turn the heater on. I've checked there, and it consumes 3 milliamps at 12 volts when the heater is powered up. So that's the signal wiring. Now we then have over here on the left 3 wires for power, and there's basically 2 black and 1 red. Now the scenario there is that the red is your traction positive and one of the blacks is your traction ground. The other black is a kind of an earth connection that goes onto the body of the pump, or the heater, sorry. So in order to discover which is which, it's just a very simple case. Just take a multimeter, touch one probe just on a continuity test, touch a probe onto the brass hose tail, and you can find out very easily which one is the ground. So that's a kind of a close-up view. I've got it here on the bench where I can supply 12 volts to the signal input, and I can supply about 30 or 40 volts from a bench power supply just to the traction input, and we'll be able to see if the unit works just even on a low voltage here, just to check that it'll draw current from the traction side when we apply 12 volts to our signal cables here. Okay, so I've got my high voltage power supply turned on. I don't have the 12 volt feed on yet. Just going to put a DC clamp meter across here, so we're not drawing any current at the minute. I'm going to throw on the 12 volts signal power, and straight away we can see we're just drawing about just a little over 3.3 amps. And if I turn off my 12 volts, that goes away, and 12 volts back on, and we're all set. We're at about 35 volts DC there, and about 3.3-ish amps. So that's it. That's a first bench test to actually verify that the unit works as it should. So at least that means the heating element, the power electronics and everything else is working pretty much as it should. So my next part of the plan is going to be to obviously make these on here with some extension leads properly onto the traction power, and we'll rig up a little test with a water tank, and we'll pump some fluid through it, put some higher voltage to the thing, and check that it's actually heating water before we start looking at mounting it in the car. Stay with us. Alright, sports fans, we are back in the workshop, and as I hope you can hear, we got some water circulating here. So what I've done is I have rigged up a plastic container just with a hose tail in it, coming down, feeding water into our pad pump, through our heater, back out through the blue hose, and it's just going in through the top of the container. It's 90mm hose. Fortunately my little pump is running perfectly now, drawing about 1 amp at 12 volts. I've also gone ahead and lengthened the power and ground cables here with some 6 square black and red and some 1.5 earth for when we're installing in the car. So we've got the water circulating, and we got no leaks, which is good news indeed. I have a thermocouple probe down into the water in this container, currently reading 19.7 degrees centigrade. I have another thermocouple just hanging down here for external temperature, and that's bang on 19.7 as well. So yeah, it is a warm day for sure. Also rather humid, so I figured best time to be doing the heating is when it's warm and the aircon when it's cold. Got my cables coming back over here now, and I want to just run through what I'm doing here to supply high voltage power, because it does have some bearing on one of the things that interested me the most in this particular heater, which was the aforementioned very wide voltage range under which it can actually operate. You see, 200 to 450 volts DC also encompasses, as you might guess, 320 volts DC. And that's the peak voltage that you get if you rectify 230 volts AC mains. And one of the things that I want to implement with this heater is the ability to heat the cabin of the car when the car is plugged into the mains on charge using mains power. So what we're doing here today is, let me just pan over a little bit this way and see if we can get some tilting action. High quality camera work as always. We've a 32 amp single phase feed coming here into a 35 amp rectifier we've just mounted on a little heatsink, and we've taken our positive and ground straight from that rectifier's DC side straight into our heater. So what we're looking for today is to see if we can warm up this tank of water here. There's about 6, maybe 7 litres in it, in the entire system, from our mains power source. If we're successful with that, then we know that we can implement this system when the heater is installed in the car, and it'll be a good test as well to see that everything works as it should before we go to the hassle of installing it into the car. So one word of caution, folks, dealing with some pretty high powers here, so the possibility of a boom shakalaka is pretty high, so you know, probably best if you get the old safety glasses on, and let's see what happens. So got our clamp meter, 0 amps at the minute, and here comes the power, 19.8 degrees in the water. Okay, we're just now drawing current. We're drawing 16, 17 amps. It's kind of jumping around a bit, as you'd expect. Oh, temperature is increasing rapidly. Wow, 21 degrees, 21.4 degrees. Must have just got a slug of hot water. 21.5. Oh, we're heating up here. 23.1 degrees. Wow. 14 amps. It's kind of jumping around. Now at 25 degrees in the tank. $27.6. Probably a bit too cold yet to feel it coming out warm. Get about 15 to 17 amps DC going in. It's probably jumping around a bit because we're using unrectified AC here. Well, unsmoothed rectified DC, don't mind me. I'm having a bad hair day. When you have as little hair as mine, that's pretty much every day. 31 degrees in the tank. It's supposed to heat to 70 degrees. I'm not sure if my plastic container will be happy with 70 degree water in it, but we'll endeavour to persevere. 34.8 degrees, 35 degrees. Should be able to detect warmth coming out of here. Oh yeah. Yeah, that's starting to warm up alright. Why don't you guys keep an eye on the time for me there and tell me how long it takes to heat this amount of water. Just probably close enough to what will be in the system when it's in the car by the time the heater core is filled up and all the other elements. Still about 15 amps, 40 degrees centigrade now. A little bit of warmth in the heatsink on the rectifier, but nothing major. Portion effect of the humidity that we have now as my safety glasses keep fogging up. So 41 degrees in our tank. This is better than watching paint dry, isn't it? .44 degrees. Oh yeah, I definitely feel that's warming up. Quite a bit of dirt going around the holes there, probably from the tank to be honest. Oh yeah, that's nice and warm in here now, wow. 47, 48 degrees, 50 degrees. I suppose keeping in mind we are starting from a warm ambient. So my idea here is I'm going to run a kilovac, obviously a fuse between the traction circuit and my heater positive. And what I'm going to do is I'm going to connect my rectifier ground to my traction ground and my rectifier positive to the heater after the kilovac. Now, because the rectifier is basically a combination of diodes, current can't flow back through it when the heater is being powered by traction. And when I have my car switched off, obviously then I can run the heater by supplying current from the mains to the rectifier, and we should be able to then use both power sources to heat the water. We're at 59.8 degrees, folks. 59.9. Oh yeah. Oh, that's warming things up now. Alright. Just hope this old tank can take it. I'm not sure what the material is. 65 degrees in the tank. It's not buckling as yet, so we'll keep going. 66 degrees. A little bit of warmth in the rectifier heatsink there now, alright, but nothing to be concerned with. 68 degrees. 70 degrees. I like to think that our regulator circuit will start pulling back now on the power once it stabilizes at around 70 degrees. Seeing 72 degrees on the thermocouple, but would be just a spike. Oh, that is warm. Wow. That's warm. Both of these tubes are now very warm indeed. Well, the body of the unit isn't really warm at all, which is good news from the insulation perspective, I suppose. I'm seeing 74 degrees on my thermocouple. 75, 77 degrees. No sign of that current dropping back. I'm going to have to shut this off when we hit 80. I don't want to completely kill it. Still drawing the same power from the mains. So it looks like we found one potential issue. 81, oh there, 81 degrees here now. Things are very warm indeed here. Yeah, there's 80 degrees, folks. Yeah, that's roasting now, alright. Oh, current's just gone to 0. Wow, okay, nice one. Looks like the bit of overshoot, probably not such a bad thing, just make sure that it's above the temperature for a certain period of time, but our current is just falling to 0. According to the thermocouple, our water is at just under 84 degrees. So that's good. We've just done a successful heat up. Now obviously in the car we'll have a fan on the radiator for the cabin heater, so that'll be cooling that water down quite rapidly. We don't have that facility here, so it'll be just more so evaporative cooling and so forth. It'll be cooling off that tank of water. So yeah, pretty happy with that. Able to heat it up just from the mains, just some straight rectified mains, no need for any capacitance in there. I might put in, I might just bang in a transorb and maybe a little X-cap in there just to soak up any nasty spikes that might be around. Don't want them messing up the control circuit in the little heater. But that's about it, folks. We got looks like we got ourselves a fluid heater solution. So next installment in this series then will be to get it installed in the car. So as always, thanks for watching, thanks for subscribing. Don't forget to subscribe if you're a new viewer. You know, God help you if you've managed to wade through this much stuff today. And yeah, so we'll be back soon when we got this thing installed in the car, and we'll be going through the procedure to achieve that. So thanks a lot, folks, and talk to you all soon.